Okay, hello everyone. I'm Wang Genshi from Big Fish. Yeah, our Big Fish is a semiconductor company located in Beijing and Nanjing, China. We just focus on AI and IoT chip and product solution. We have the capability of developing SoC, software and OS development, and modem communication technology, and software, hardware, system integration, and design of 2B2C products. And our products include mobile, UAV, and super Ethernet and IoT. So today, I would just share my experience about RDC. So what is RDC? RDC is an alias of reset domain crossing. So usually we pay much attention on clock domain crossing, but actually mistakes or problems often happen also on reset domain crossing. So in our product, we find that much attention or hard work should be paid to the reset related problems or errors or something will happen on reset. So when it comes to RDC, usually we first question is why we need RDC. RDC is similar to clock domain crossing. Asynchronous reset releasing may cause a recovery, remove violations, or set up hold check, which may result in metastability and may cause functional failures or possible silicon damage. Because of the attribute of asynchronous crossing, simulation cannot reliably catch RDC errors. So therefore, and in the complete and reliable SoC development, RDC verification is necessary. We need static and formal methods which can deterministically identify RDC issues. Whenever there is a reset crossing from one domain to another, there is an RDC. So let's take an example by the picture of the left side. The flip-flop R1 is reset by RST1 and R2 reset by RST2. They are asynchronous. So when RST1 asserts and RST2 stays stable, R1 may generate an asynchronous edge that violates setup hold window of R2, so which may let R2 go metastable, just like the picture of the right side. So here is an example of design techniques to avoid metastability in the reset of R2. If the reset of R2 asserts before R1, R2 will not sample metadata because when there is an asynchronous edge caused by RST1, R2 is in reset mode. So of course, there are other techniques to handle RDC issues. Let's take an example by the picture of the left side. Before the asynchronous assertion of R1, the clock of R2 is gated. So even there is an asynchronous edge when RST1 asserts R2 will not see metastability. This kind of method is often named clock isolation. Similarly, we can also use the technology of data isolation. Before the assertion of RST1, as long as the data path from R1 to R2 isolated, R2 will not be affected by any asynchronous reset assertion of R1. So here is some real-world RDC issues examples. If RST1 asserts before RST2, F1 will generate an asynchronous signal, and F2 may go metastable. And if either function RST1 or POR asserts before function RST2, then F1 will generate an asynchronous edge, and the destination register F2 may go metastable. So here is another. This example illustrates a reset tree integrity issue. The reset assertion of the left side register combinationally combines with the clock network and generates a glitch clock into the receiving register. And this glitch may cause a functional failure. And here is some safe RDC examples. Here are examples. And so the first case, RST1 still asserts before RST2, although there is an RDC path between F1 and F2, and the assertion of the reset at F1 will cause metastability on F2, but the metastability from F1 to F2 to F3 is blocked because F3 is already in reset mode. And the second case, assertion of the reset on the transmitting register will always cause the assertion of the reset at receiving register. For example, there is never a case where F1 reset asserts and F2 reset is not asserted. So in these slides, we can see some recommended RDC verification methodology. And our tool, we use Mentor Questa RDC tool. The both RTL and constraints are needed by the tool. The tool first executes a static check, which will verify the integrity of the design as well as the reset tree. So here I want to say the reset tree is the same as important as the clock tree. They are both. So we analyze the reset tree in our SoC designs, and no matter the design used for bus matrix or the CPUs or some hard blocks, hard cores, or the modem modules of the in the system. So the second, then the embedded formal checks will verify the correctness of the RDC path. And the use of both static checks and formal functional checks provide lower noise and a better quality of results. So we compared some different tools from different EDA vendors, and at last we find that Mentor Questa RDC give a pretty good flow and results. It should be cared that constraints guide the RDC verification and should also be verified separately. This just like we do the SDA, we should make sure that our constraints should be given correctly to the tool. And in these slides, we can see the RDC verification preparation. If the RDC verification readiness is not verified, and the RDC verification environment may not be clean, and this may lead to noisy results. The step of static check will also automatically generate constraint templates. For example, reset order constraints, we can use the templates to write our constraints. The isolation enables are verified by functional checks to ensure that the isolation signals will block the transmission of the data and the clocks. And in this slide, we will give some case of some study, some case in the project usage. So we will see some cases found and fixed in our RDC tool flow. The first case is related to glitches core to specific state machine, and the second case relates to RDC tool about asynchronous FIFO usage. We can see how RDC verification identified a violation due to missing constraints. And so, as you can see from this picture, we can see that the C state is a multi-bit state machine, and combinationally combine the asynchronous reset for register work flag. When the state machine goes to some specific state, a glitch may occur because it is combinational logic, and the flop work flag behaves out of expectation because of RDC issue. Code review will probably miss these kind of issues, and simulation is not inefficient, may also miss it. But by static check, RDC tool will identify them. So RDC static check is more efficient than finding issues by simulation and code review, and will find issues earlier in the design flow. For example, compared by simulation. Furthermore, simulation may miss these kind of issues. So as you can see that this kind of issues is found by the check of tool. And in this slide, we can see the FIFO issue. The two resets of the asynchronous FIFO are from different sources. By doing RDC static check, violations are reported. So designers know the violation on one side of the asynchronous FIFO reset asserted. Maybe this side is asserted while the other side is not, which may cause error. This kind of errors may in our project, this kind of errors is come in one of our project. We found it exists by the MASIM flow, and a block power down, and one side of the FIFO reset, and the other side not. So this kind of error, if we use our RDC tool, so this can be found earlier. So let's give some summary. Let's do some summary. So reset architectures are too complex to verify by inspection. So an RDC verification methodology is needed. So RDC verification methodology enables more complete and efficient reset and RDC verification. So methodologies provide metrics to measure verification progress and completion. So designers will know when verification is sufficient for tape out. By using RDC static and formal check tool, project goal will be reached for eliminating reset and RDC issues. So that is my presentation. Thanks.
Thank you very much, Shiwang. And yeah, thanks a lot for giving the overview how you tackled reset domain crossing verification in your projects. Are there any questions to Shiwang? So one question was just popped up from Norbert Förster, I think. Which tools and which formal language did you use? Can you elaborate a bit if they run out of the box or if there's a lot of customization needed?
Mm-hmm. We use a Mentor Questa formal tool.
And the question was also asking whether it's whether this runs out of the box or whether you need a lot of customization for this.
Well, as actually the constants is quite easy. If the system SoC system is very big, sometimes we can just use some extracted model, just like the ETM from STA flow. Just we can just write some constants that just tell the tool the boundary clock reset domain or clock domain constants or attribute. It can be faster.
And could you give us an indication like how much effort this is to set this up?
I think in a SoC, in a complicated SoC, large scale, maybe 1 week is enough.
1 week. Okay, so
yes.
Okay.
Yeah.
Okay, thank you. There is a question from Tibor Futo asking whether you have more use cases that you tested the tool on. Hope I grasped this question. It's actually not a question. It's more a comment, I think. Hopefully I interpreted this correctly. I'm not so 100% sure. So do you have more use cases where you applied this technique?
Okay, the techniques. One is about I think the bus matrix may should take care. Yeah, and you may in I think, yeah, I know that some company use ARM Ember designer to generate bus matrix, and some use the NIU knock bus matrix. So sometimes the reset problems will happen, and we can extract, and we should take care about the bus matrix, and we make sure that the reset will be done enough on the bus. Sometimes maybe one part of the bus matrix bus is resetted and other port not resetted, and errors will happen. So maybe you can, my suggestion is maybe you can just make it easy, that make it and write just a model of the bus.
Yeah. Okay. Tibor, I posted in the chat, maybe your question or your comment is maybe better handled as in a direct discussion of the record, because it's kind of difficult for me to moderate that, frankly speaking. And I'm also not sure if we have the infrastructure here to draw real world applications and so on. I mean, you would probably need a whiteboard or something. There was one more question from Pomoran Seki. Did you evaluate other tools?
Okay, yeah, actually, I also evaluated a spyglass from Synopsys, and yeah, maybe because I used the Mentor Quest before it is called, not it's called Quest, it is called Zeroin, and I used it many years, and find it it's easy to use, and the report is quite simple, and we can ready to use. and the FSM state machine related error is found by the theory. And maybe Spyglass can also have some other constraints which can find this kind of error. But by now, I have not found it by that tool. And maybe I will do more study of that tool. Yeah.
All right. Do you plan to join the virtual world later on during the day so that maybe Tibor and Ayari, who are commenting, and maybe also Takara can have a face-to-face discussion with you?
Yeah, you can my mail. You can I think if anybody have some questions about this topic, I'm very happy to communicate with them.
Okay. Would be still great if you could also join the virtual world later on. All right. Are there any more questions on the from the auditorium? No new chat messages popping up, I think.
And my mail. I think my mail is you can see my mail from the paper. If anybody have some questions, we can also communicate by mail.
Yeah. Cool. Good. Then I suggest that we make a short 3 minutes break now to just synchronize the schedules of the sessions. Maybe some people want to move from one session to the other session. So I don't want to kick off the presentation too early. Thank you very much, Wang Zhen. Thanks for presenting.